Welcome to S Chemistry. I am your instructor Dr. Suhas Gaudi. I will be teaching you B.Sc 5th semester Physical Chemistry course on Elementary Quantum Mechanics. Here is the outline. So in this lecture, I am going to cover Schrodinger wave equation for hydrogen atom in three-dimensional and separation into three equations. Schrodinger wave equation for hydrogen atom. So hydrogen is a simplest atom of all atom, and it is a three-dimensional system, and the Schrodinger equation for this system is h psi equal to E psi, where h is the operator, psi is the wave function, and E is the corresponding energy of eigenvalue of a eigen equation. So where h is the Hermitian operator, that is the value of h equal to minus h cross square divided by 2m, and the inverted triangle is the operator. That operator is Laplacian. So Laplacian square plus v, the potential energy with three Cartesian coordinates x, y, and z, where the Laplacian operator in each Cartesian coordinate is given by del square by del x square plus del square by del y square plus del square by del z square. So the potential energy of interaction between electron and the nucleus is given by, that is they represented by V, capital V, that is the potential energy in the with R, that is a radial vector, that is equal to minus z e square divided by 4 pi epsilon naught r. So here E is the charge on proton, epsilon naught is the permittivity of free space, r is the distance between electron and proton, and the factor 4 pi epsilon naught arises because we are using SI units. So from this, since this attractive potential has spherical symmetry depending only upon r, and it is convenient to express Schrodinger equation in terms of polar coordinates rather than Cartesian coordinates. So in this, for this equation we are going to use polar coordinates, that is r, that equation will be in terms of r, theta, and phi. So the Cartesian coordinates x, y, z are related to the hydrogen atom, and when it to the polar coordinates, it look like over here like this. So where x is equal to r sine theta cos phi, y equal to r sine theta sine phi, and z equal to r cos theta. So in right hand side you can see in this figure. So P is the your point of where electron is located over there, and O is the your nucleus. So this distance is r. So this is a radial vector. So the angle between z axis and the OP line. So this angle is, we call it theta, and the second parameter. And the third parameter of polar coordinate is the where tangential here this p equal to r sine theta. So here this angle comes as a phi. So this is nothing but your projection of p at xy plane. So that's why this come as a phi angle. So using these all trigonometric values, so you will get x, y, and z. From this, um, the Schrodinger equation of hydrogen atom in terms of polar coordinates, it becomes in this way. So you will have the h cross square divided by 2 mu r square. So here is the common constant over here, and the first derivative is the related to the r radial vector. Second derivative is related to the sine theta, that is d by d theta, and the third differential parameter is related to del square by del phi square. So here remaining things are related to its common. So this term is shows as a potential energy into psi. So this psi equal to E psi. So in previous slides we have seen H psi equal to E psi. So this whole term represent as a H, where Hermitian operator contains the energy terms as well as potential energy. So where in this case mu is the reduced mass of the electron and the nucleus. So that is mu equal to mass of electron into mass of neutron divided by mass of electron plus mass of neutron. So here n should be there. So here psi is a function of r, theta and phi. So psi can be expressed as psi r theta phi equal to this is a radial vector. Independently you can mention as a function. R is a function of radial only. Phi theta is a function of theta only, and phi is a function of phi only. So if you multiply it all three, you will get the equation number 2. So where r is the radial function, which is a function of r only, and these two are the angular function. So substituting equation 2 into equation 1, you will get three different separated equation. So here I'm not going to show how it came. I'm just giving the direct equation. Mm, so here first term is related to your r, second term is related to your this r with respect to the small r, and the third term is also related to the energy and potential energy. So this is the function of only r only. The second is related to only theta, and third is related to only phi. So this all three equation comes after solving these equations. So where m and beta are the constant in these equations. Now we are going to see quantum number and their importance. So the solution of a Schrodinger wave equation for hydrogen atom yields three quantum number, that is n, l and m. So first we will see n. The n we say the principal quantum number. So it determines to a large extent the energy of an electron and the average distance of electron from the nucleus. So atom has three different types of energy. So here the n is determines the that principal quantum number determines the energy of an electron and the average distance between electron from the nucleus. So as the n increases, so the value of n goes as n increases, the electron gets further away from the nucleus and its energy increases. So a portion of this energy is, however, as associated with the orbital motion of the electron around the nucleus. So this orbital motion is described by angular momentum. Now we are going to see the second quantum number, that is L, that is a azimuthal quantum number. So this quantum number accounts for accounts for appearance of a group of closely spaced line in the hydrogen spectra. So in hydrogen spectra, the group of closely spaced line we have observed, that we have seen. So but the energy associated with angular momentum of an electron must be well within its total energy determined by n. So this L is always come under the total energy of determined by L, which is determined by L. So the electron in atom are grouped not only into main energy levels given by N, but also into energy sublevels given by L. So the value of L gives the subshell in which the electron is located. The value of L gives the subshell in which the electron is located, and it is also determine the shape of the orbitals in which the electron is located. So the number of subshell within a principal shell are determined by value of n, that principal energy level. So thus L may have all possible whole number values from 0 to n minus 1. So the various subshells, sublevels are designated as S, P, D, F. So according to as the value of L is equal to 0, 1, 2 and 3 respectively. Now we will see the fourth quantum number, third quantum number, that is m. So we represent as the magnetic quantum number. So since an electron has an angular momentum, its motion may be linked to the flow of electric current through a loop. Such flow of current as is well known creates a magnetic field. So this field can interact with an external magnetic field or electric field. So as a result of their interaction, we get this. So the energy, the electron in a given energy sublevels orient themselves in a certain specific regions of a space are the nucleus. So these regions of a space are called orbitals. So the number of orbitals in a given energy sublevels within a principal energy level is given by the magnetic quantum number m. So the number of value allowed to m depends on the value of L, and it is known from theory as well as experiment that the possible value of m range from minus L to 0 to plus L. So this is the range. So total we will have 2L plus 1 values. So this is the range of a magnetic quantum number. Now the fourth quantum number is the S, the spin quantum number. So the spin quantum number does not follow from the wave mechanical treatment. So it's independent of wave mechanical treatment, but it is will be there. So the electron possesses an intrinsic angular momentum or a spin specified by, so the quantum number s equal to half. So the value of s is equal to always half. So the related spin angular momentum has the magnitude. So to calculate the magnitude, you will have this formula. So the capital S equal to in bracket small s into in bracket s plus 1. So the whole this whole term comes under um, the power of half. So this is under root square root actually. So this into h cross. So if you put this s value half into here, you will get this value. So under root 3 divided by 2 into h cross. So that is the actual magnetic magnitude of the spin angular momentum. So now this is the relation between angular momentum quantum number L and the orbital angular momentum capital L. So from small l we will calculate the big L. So that is the orbital angular momentum. So here this is the magnitude. So in bracket you will have L into L plus 1, the bracket close, the power of half, so into h cross. So if you put this value, you will get the corresponding orbital angular momentum. So for now we came to the end of this chapter. So thank you for watching, and see you in next lecture. Till then, happy learning.